This video is part of a course on food physics, of which this is the applications section. This is the second video of the series, but it is the first video of the three ways to approach the physics of air drying. So it's the first one and the most comprehensive way to see the physics of air drying. And here are the learning outcomes for this series of videos on air drying. These have been discussed in the first video of this series, so I will not get into more details. Feel free to pause the video and look at the learning outcomes. Of the three ways to study the physics of air drying, starting from the least mechanistic to progressively more mechanistic ones, we are going to start with the most mechanistic one that is also the most comprehensive and most detailed, and go down this path to lesser mechanistic ones. Why? So that when we do the less mechanistic ones, we know exactly what types of assumptions have been made or implied in the less mechanistic ones. So the content is divided into 4 parts. First, we put together all the physics of air drying that we put together to build a model, and we then use this model to do simulations to learn more about the spatial and time variations of different quantities, and then we learn about the effect of different process parameters like drying temperature, for example. And finally, once we know enough about air drying, we try to see how the same physics, the same understanding can be extrapolated to other drying or drying-like processes. So what is the physics of air drying? To do this, we want to look at the food as a porous medium with solids having pores in which water, vapor, and air transport, as kind of shown in a schematic here. So, of course, the food dries, so it loses water. And so there must be mass transfer. And the mass transfer can be in two modes. Either things can be flowing or it can be diffusing. There is also heat transport, this one, but this we will come back. The three phases we are interested in are water, vapor, and air. Whether we like it or not, there's going to be some air in there. So now the cause of flow, the transport, is two kinds. One is flow and the other is diffusive. So the flow is due to pressures developed inside. And how does pressure develop? There is evaporation inside. There's evaporation inside that causes the pressure generation. That's one source of pressure generation. You can also have gas generation, like carbon dioxide generation in a food, but in this case, just for simple air drying, it can be due to evaporation. But when these drying air temperatures are not way too high and the drying is kind of reasonably mild, then there isn't as much vapor generation, or there isn't as much rapid vapor generation, so there is not as much pressure development, And so this pressure driven flow is something we're going to ignore for our study of air drying in this case. This is only true when it's not very intensive heating. If the heating is very intensive, this assumption will need to be modified. So then we ignore gas pressure driven flow for both vapor, air, and water. And these other terms like swelling pressure or gravity are ignored anyway. So this is ignored. All of these are ignored. The other type of transport is diffusional. So for water, capillarity is the driving force, which can be shown to be diffusion like, and then vapor and air, they will both be moving by molecular diffusion. We then get into the source term, and the source term is due to evaporation. So for water, you have a negative term because we're losing water by evaporation. And then for vapor, we have a positive term because it's generating vapor. We then come to the heat part. And so heat transfer will of course happen in all of the phases: water, vapor, air, but also the solid phases, the solid phase. Okay, and so the driving force for heat would be conduction in all of these phases: solid, liquid, water, vapor, and air. In addition, transport of water and vapor plus air, as they're moving, they're carrying energy. So this would need to be considered. Finally, evaporation, that is really distributed throughout the food material. It may be more near the surface where the temperature may be higher, or higher somewhere else, but really it's throughout the material, throughout the food, there is going to be different amounts of evaporation. So that will need to be considered. So this plus the evaporation. So now to summarize then, included physics are capillary diffusion of water, molecular diffusion of water, vapor, and air, evaporation, and heat conduction in solid, liquid, and vapor and air phases. So the physical processes that we described, like capillarity or diffusion, are combined with mass conservation and energy conservation to arrive at the full physical or mathematical description of this air drying process. Now, the equations that are shown here are derived in full detail from scratch in a separate place. So this is in our theory section, and under the theory section you can look into the equations for porous media. So here we're just sharing those equations and customizing those equations for air drying. So let's say for water then, we have a transient term, and then the flow, because we included capillarity as part of diffusion, and we said that the pressures are not very high, so the pressure driven flow is important. So then this one is ignored, and here we have the capillary diffusion, and then this one is the evaporation, water changing to vapor. Likewise, for the vapor, we have the transient term, and we ignore the flow, that's the next term, and then we have molecular diffusion and a source term for vapor, because vapor is generated. Now, because we are staying at 1 atmosphere, this is an assumption that we're not producing vapor too rapidly inside the food, then we don't need the pressure equation, which is a combined vapor plus air equation. Instead, we can get air from simply just saying air, partial pressure of air and vapor make up 1 atmosphere. Okay, so from there we can get the amount of air. The heat equation also has the transient term and convective transport. That means when fluid is moving, so in this case by capillarity for water and by molecular diffusion for the gas phase, they are carrying energy, so that is included in our physics. And then the combined conduction, because it's very hard to treat conduction in individual phases separately, so solid, liquid water, vapor, and air, they're all combined in the conduction term with an effective thermal conductivity that is weighted by how much of each phase is there multiplied by the conductivity of individual phases, and then evaporation term. Okay, and so again, this one we ignore generation of heat because we're doing simple air drying. If we did microwave drying, then that term would be there, but now we are ignoring that one. You notice that the I dot, the evaporation term, that strongly couples the heat equation with these other equations, water, vapor, and so on, because the I dot involves latent heat, so it is in the heat equation, but then I dot is the source term for vapor and the sink term for liquid. So the heat equation and the mass equations are strongly coupled. This makes this type of physics to be complex and interesting. As the food dries, it loses water and therefore it shrinks. Now, is the decrease in volume of the food, that's the shrinkage, the same amount as the volume of water lost? What do you think? You can pause the video to think about possible answers. So here is the answer. The matrix tries to collapse by the same amount as the amount of water removed. However, the matrix is constrained by itself. So even though it tries to shrink as much, it cannot. It produces stresses in the solid, and the final reduction in volume can be less than the amount of water lost. We will describe this in more detail later on in this video. So the total shrinkage or deformation at any location is given by the moisture driven change, that is the driving force, and the restraining effect of the solid. Now, if we write the equations of mechanical equilibrium, we relate the stress on the solid skeleton to total deformation. Now, the total deformation is made up of this moisture driven deformation and the restraining effect of the solid. If we are, we are skipping these details to reduce complexity, but anyone interested in these details, they can be seen in their full glory in the series of videos in Porous Media in a separate series. And in that series, if you look under deformation, you can find all of the details there. The material model, how the material behaves mechanically, that can be elastic or more complex, such as viscoelastic. Also, because shrinkage due to drying involves very large changes in the size, so we have to use special physics to compute, also called the physics of large deformation. So the moisture loss calculated from the heat and mass transfer model described in the previous slide feeds into this physics, and from here we can compute, we can get what is the change in size. This is mechanistic way of obtaining the deformation. So after implementing all that physics we discussed into a model, we now want to use the model to simulate and learn about air drying and the different physics in it. That's what we will discuss now. So all the physics that we described and its accompanying model equations applied to a cylindrical disk of potato gives us these simulation results that you are seeing in the animation. We are now going to look into it in a lot more detail. So first, there is the transient temperature plot. So the transient temperature is definitely diffusion-like, but it rises to some temperature below the drying temperature. The drying temperature in this case is 70 degrees. So it becomes asymptote toward what's called the wet bulb temperature when there is quite a bit of water left. Now with time, much later when there is very little water left, then the temperature will start to rise to the drying air temperature. Now these simulations were not carried out that long, so you're not seeing that in here. And here is the average moisture content. You notice it is dropping with time, and also the rate of this moisture loss, that also drops with time, meaning this curve kind of slows down here. That's because as it loses moisture, then the driving force between the moisture in the food and the surrounding air, that driving force is also going down. So the rate of moisture loss is also going down, which will come back in a second. As you increase the temperature, then of course on the surface, then it's going to be maintained at a lower moisture, but also at the higher temperature, everywhere inside, water can evaporate more easily. So you remember we talked about this I dot term, the rate of evaporation, that will increase everywhere. So because of that, altogether the evaporation, the loss of moisture is much faster. So the drying is faster at the higher temperature. Although not shown here, instead of increasing drying temperature, if we increase air speed at the surface, it will have a similar effect of faster drying due to reduced heat and moisture transfer resistance. Now, from this average moisture, as it changes with drying time, I can calculate the rate of drying, defined as the time rate of moisture loss divided by the surface area, as shown in this figure. So this is now drying rate with moisture content. So the rate of drying first increases. As you can see, first it increases, then because the material is heating up, so evaporation is easier. Then it becomes somewhat steady, approximately corresponding to the wet bulb temperature. Then it starts to drop, and it starts to drop because there's now simply less moisture there. So this exact same process you can see at a lower temperature, and then everything, the drying rates are lower, meaning the material will not dry as easily. So looking at this simulation again, here you can see the size changes and the colors correspond to moisture level, which is the scale here. So you can see that the moisture is not going down uniformly everywhere. The moisture loss is more near the surface. So as the moisture level changes, the height goes down. The height goes down, and as the moisture level changes, the diameter goes down. However, because moisture is not uh, being lost uniformly throughout the food, it's going to shrink different amounts at different places. And you can see from the animation that more moisture again is lost from the surface, where we expect more shrinkage. This will be discussed in more detail later. In addition to the temperature change, the moisture loss, and the resulting shrinkage, related to all that, there is another critical aspect of this drawing, and that is the material itself is changing intrinsically, changing its properties. This is understood using what's called glass transition. So if you take a food material and as it's being dried, so let's say it's moving in this direction and losing moisture, then at some point it changes state from rubbery on the right hand side to glassy on the left hand side. And this transition, the temperature at which the transition occurs, of course depends on the product temperature. So at higher product temperatures, it's going to need much more drying to get to this glassy state. Why are we talking about this? Because in the rubbery state, the material is soft, whereas the glassy state, the material is hard. So this great change in mechanical properties is shown in the right figure. So as the moisture is going down, the modulus is going up. And this is a big deal in terms of how the shape changes. This big change in property as the material goes from rubbery to glassy is not going to happen uniformly throughout the material. Why? Because as shown in this animation, that the moisture levels are different at different locations. And of course, temperatures are also different at different locations. So if we look at the variables, let's say moisture in this cylindrical disk of potato being dried, we see that the changes are not uniform everywhere and it changes with time. So first, there is more moisture loss near the surface, leading to more shrinkage near the surface. But this dried material is harder based on discussion earlier. This harder material resists shrinkage. This is the most important part. The harder material resists shrinkage. As you can see from the simulation, that the shrinkage, if we let it go, it eventually kind of stops. So the important note here that we did not input shrinkage. So the shrinkage that you see, the different rates, initially higher and then it's slowing down, we did not input this from experiment or something else. Our physics framework allows us to calculate shrinkage from moisture loss and the mechanics that we discussed earlier. So why does the shrinkage stop? As we lose more moisture near the surface, more shrinkage happens near the surface, but the dried material is also becoming harder. This makes the shrinkage eventually stop. That is really the mechanism by which the dried materials, the dried material restrains shrinkage. As it's drying, the formation of the harder shell near the surface is what restrains the material. It makes it stop shrinking as much, and eventually it stops shrinking at some point in drying. This shell near the surface is termed case hardening. So the physics that we talked about, temperature change, moisture change, shrinkage, and so on, how are they being affected by the process temperature? That's the physics we're going to talk next. We know the food material shrinks as it dries, but the amount of shrinkage, does it depend on the drying rate? I would like you to think about this for a few minutes, so just pause the video and then come back to it. As we reduce moisture, as we go down this way, then the volume goes down, as you can see in this curve. For this low temperature or lower drying rate, this shrinkage is linear or called almost ideal. What that means is the volume change, the change in volume as it goes this way, it pretty much equates the change in volume of water lost. Only near the end here, it deviates from this linearity, it deviates from this ideal shrinkage when the material has gotten harder, that even if we reduce moisture, like here, even if we reduce moisture, the material in its current glassy and hard state, it's not able to reduce the volume as much. What's not shown here is at this lower temperature drying rate, most of the material changes to glassy state near simultaneously at this slower process. In contrast, at this higher rate of drying at a higher temperature, the surface becomes dries out much quicker, and therefore it enters the glassy state, while the core still has quite a bit of water and it stays rubbery and therefore soft. However, since the outer material has dried out and become harder, then it resists shrinkage, and the piece as a whole does not shrink as much. So, for faster drying, shrinkage near the surface deviates earlier from ideal shrinkage, becoming hard and glassy and leading to more case hardening at the higher temperature drying. Even more details of this physics is explained in the original work of Dr. Gulati that you can read up for further details. So the higher temperature drying causes the outer crust to form sooner, and this leads to more case hardening. Now this crust formation or case hardening, how it varies from the outer areas to the inside of the food is shown in this plot here. So the plot shows the difference between temperature at a location and the glass transition temperature at that location. Now the glass transition temperature itself depends on the moisture level and the temperature at that location. This left figure here shows for early times during drying. At this early time, at the higher temperature or faster drying, there is a thin crust forming on the surface. Since the moisture is low in this dried thin outer layer, the glass transition temperature for that layer is very high, much higher than the actual temperature, making the material glassy. This higher drying rate happens due to either the temperature or higher velocities that increase the heat and mass transfer coefficients. Most of the material is green. It means that it is wet and rubbery because these locations did not dry much. At these higher moisture contents, the glass transition temperature is much lower. So temperatures much higher than glass transition temperature makes the material stay in rubbery state. Now on the right side is the same plot but at later stages of drying. You can see the spatial distribution of rubbery versus glassy. So red being glassy and green means rubbery. This spatial distribution of that is quite a bit different at these late stages of drying. For a high drying rate, that's this one, relatively more of the outer regions get dried, whereas some of the core is still wet, as you can see in green. It stays in green because with higher moisture, the glass transition temperatures are lower, and therefore the material stays in the rubbery state. All that was for a high drying rate. For a low drying rate, that is drying at the lower temperature, at these late stages, the material has dried more uniformly to the lower moisture. So as you can see here, to the lower moisture that corresponds to high glass transition temperatures, and therefore the entire material is at glassy state, both cases. This crust formation near the surface, as you can see here, the red part, that may be desirable or undesirable. So if we want to rehydrate this dried material, then a crust is undesirable because crust has low permeability. It will have lower permeability to water. But suppose we are doing drying as a precursor to, let's say, puffing the material. So in that case, forming a crust, as it's seen here, is good because that crust would be relatively impermeable, and in a puffing process, when we heat the inside and generate a lot of vapor, that vapor would have hard time releasing, so it will generate more pressure, so it will puff better. So then for puffing, we do want the crust. So whether the crust is desirable or undesirable depends on the application. This case hardening affects the important quality property of food, that is porosity, which is the fraction of volume occupied by the gas. Here we want to see how the porosity develops with drying and how this development is affected by the drying temperatures or the rates of drying. So this is one, and this is the lower one. At higher moisture levels, here the material is rubbery and it can shrink. So the volume can collapse by the same amount as the moisture loss. That is, all the lost volume is replaced by the remaining material, so the porosity does not develop. On the other hand, in this low moisture region here, the material becomes glassy, restricting its shrinkage due to hard outer shell and leading to increasing empty space inside, because as the water is lost, it's not replaced by material, it's replaced by empty space, and therefore the material gets more porous with moisture removal. Does drying rate make a difference in this porosity formation? And let's explain that using this cartoon. So at lower drying rate, which is shown here, take that back, at the higher rate of drying, this outer layer here, it gets too dry too soon, becoming harder from the glass transition and restricting shrinkage earlier in the drying process. So it too quickly, it has an outer shell that stops or slows down further shrinking, even though there is a lot of water inside. So as it moves to a drier state, the material wouldn't shrink as much. In contrast, for a lower drying rate, not as much of this outer layer or the outer dry layer, the sort of uh, the case hardened layer does not form, so the material is rubbery anyway because it is at a higher moisture, so it can keep on shrinking, so the shrinkage can continue. So the higher temperature drying, this one, leads to a higher porosity when dried to the same moisture level. But higher porosity also means lower bulk density. To summarize then, higher drying rate, like higher temperature, would lead to early fixing of the volume. So the volume is set because of this outer shell, and that leads to the final product being more porous, and therefore it has a lower bulk density. Can a food material crack during drying? This plot shows how the maximum principal tensile stress, one of the measures of maximum stress inside the entire food material, would develop as the material is dried. So the four black lines, this one, these two, and this one, they are for four different drying conditions. And the red line, on the other hand, corresponds to a fracture stress above which a material can crack. Now, at higher rates of drying, like this one, the surface dries a lot faster and larger stresses are developed driven by larger or higher moisture gradients near the surface. Also, at low enough moisture in this region here, material transitions to glassy and thus more brittle, and so also contributing to higher stresses. So fastest drying, which is this condition, generates the largest stress. And if this stress in this region, for example, if it exceeds the fracture stress, then the material can crack. So to summarize then, higher drying rate leads to larger moisture gradient, and that leads to larger stress gradient and material cracking at the highest stresses. The final topic in this video is whether we can extrapolate some of the physics we learned to other drying or drying-like processes. The answer is yes. One of the great advantages of studying air drying that we did very mechanistically is that the principles discussed here, such as multi-phase heat and mass transfer in a porous medium and change in state of material from rubbery to glassy, and relating all of that to shrinkage and possibly cracking, all of these are useful for studying other processes and other materials. Parts of these are useful in, for example, combined drying processes like microwave drying, or other drying processes like spray drying or fluidized bed drying, including related processes that we don't call them drying, but really they are very much like a drying process, like baking or deep frying. So they all share a lot of the same physics. Now, which of the mechanisms will dominate, that depends on the type of drying. In fact, that changes the nature of drying altogether. For example, in microwave drying, pressure driven flow is very important. We neglected that here for air drying, but we cannot do so for microwave drying. So some of the same physics carry over. We can see cracks, for example, in a bread baking process, following some of the same physics that we have discussed here. Not all of it, and some other things need to be added or subtracted from the physics framework, but a lot of it, a lot of the physics we studied carries over to studying related processes. As you will see in other videos, this comprehensive mechanistic approach that we just discussed is not the only way to study drawing. So there are other mechanistic approaches. So when do we use this approach? So note that this is very, very general, so it's very widely applicable. So it's probably good for many, many drawing processes. But at the same time, this framework is complex, so it needs more training and resources. So when do we go for this kind of the type of approach that we just discussed? When do we go for it? We should go for it when we need detailed understanding. For example, if we need to understand relative transport in liquid and vapor mode, how much of the transport is happening as liquid water and how much is water vapor. If we want to really understand the drivers of shrinkage and predict shrinkage, if we want to know how the crust is forming, if we want to know and predict if in a mechanistic way the porosity and bulk density, if we want to know if there's possibilities of cracking from moisture gradients, or if we want to know in some rapid heating if there is any puffing effect, and also if we want to do microwave drying, which of course will change some of the details here, but we would be looking at this kind of an approach. So let's summarize this video. In not so intense air drying, the modes of transport of liquid water and water vapor are as follows. Liquid water is mostly by capillarity and water vapor is mostly by molecular diffusion. We can probably ignore any kind of pressure driven flow. So the moisture content goes down with time as expected, as we all know, but this rate of moisture loss is increased as we increase the drying temperature. For example, at the higher temperature of 70 degrees here, and that can be attributed to two things. One, so if this higher temperature, also it can be higher velocity, that will give higher drying rate. So two things can happen. One is the surface evaporation and removal of moisture from the surface would be easier at the higher rate of drying, and also at the higher temperature the internal evaporations would increase. These two factors would cause the higher rate of drying, so the moisture will drop faster. Now the shrinkage from moisture loss happens but it's initially proportional to the amount of water lost, only initially. But as the food material dries, its mechanical property changes quite a bit. So it becomes, at the lower moisture, it becomes harder and it resists deformation. So this harder outside shell that could form, it leads to case hardening, and this complicates the shrinkage. So at the lower moisture levels, reduction of moisture doesn't lead to the same reduction in volume of the material. Faster drying causes the harder shell to develop sooner. So there's more case hardening, reducing additional shrinkage and leading to high porosity and therefore lower bulk density. Higher drying rate also leads to higher moisture, larger moisture gradients. Higher drying rate, of course, would lead to larger moisture gradient and larger stress gradients that could lead to cracking of the food material. Finally, a lot of this physics of drying processes can be extrapolated to other drying, not just air drying, and also drying like processes like baking or frying. Now we just completed this comprehensive mechanistic approach to studying the physics of drying. In the next video, we will talk about another mechanistic approach, but lot less detailed and with lot less complications. It's still mechanistic and it is the most common approach to studying drying. However, there is no free lunch. When we go to less complex models, ignore some physics or approximate some other physics, that kind of a model will not give the same level of insight into the drying process.